Hello and welcome to episode 633 of the People Behind the Science podcast. Today we are excited to be rebroadcasting our interview with Dr. Sophia Hayes. This interview was originally published on January 9th of 2015. And listeners, Sophia is a materials scientist who's working to understand the structure and properties of different types of inorganic systems, such as semiconductors and other optically and electronically active materials. She specializes in using a technique called nuclear magnetic resonance, which is similar to magnetic resonance imaging, or MRI, to learn more about these different kinds of materials. In our interview, Sophia shared more about her life, her career, and her work. So listeners, please enjoy this episode of People Behind the Science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to another episode of People Behind the Science. I am thrilled to be here today with Dr. Sophia Hayes. So great to chat with you, Sophia. How are you?
I'm well, thank you.
Wonderful. Well, we are delighted to chat with you today. Listeners, Sophia is an associate professor in the Department of Chemistry at Washington University in St. Louis. She received her bachelor's degree in chemistry from the University of California, Berkeley, and worked for a few years afterward as an associate for a management consulting firm. Sophia interned at the Sandia National Laboratories before entering graduate school, and she received her PhD in chemistry from the University of California, Santa Barbara. She then completed a Directorate Postdoctoral Fellowship with the Livermore National Laboratory and UC Berkeley. Sophia also served as an Alexander von Humboldt Postdoctoral Research Fellow in the Department of Physics at the University of Dortmund in Germany before joining the faculty there at WashU. Now, Sophia has received a number of awards and honors during her career, including an NSF CAREER Award, a Washington University Graduate Student Senate Excellence in Mentoring Award, an Alfred Sloan Research Fellowship, and the Vold Memorial Prize from the Alpine Solid-State NMR Conference. Now, Sophia is here with us today to tell us all about her journey through life and science. So today, Sophia, we want to get to know you, both as a scientist, but also as a person. So can you take a first few minutes here in the beginning to tell us what you like to do when you're not doing science?
Oh gosh, when are we not doing science, Marie?
Right.
It's pretty much part and parcel of our everyday life. I hope I bring science into everything I do. But yes, I do spend some time outside the lab once in a while. I have a wonderful family, a husband and a daughter who has just turned 9. And, what do I do when I'm not doing research? I suppose, we like to sail. We like to ski. We're outdoorsy sorts of people. And we just adopted 2 dogs from a shelter. So we've got a pretty busy schedule with all of us considered.
Well, that sounds wonderful. What kind of dogs?
They are just mixed breed ones that were rescue dogs that came from a shelter where my daughter was volunteering for a summer. So this is a new chapter in our lives and keeping us quite busy outside of the lab.
Well, that is exciting. I know I did some volunteering as a college student for the Humane Society. It's hard not to want to come home with a dog every day.
Exactly. So we held it at 2, but nonetheless. So
Certainly.
Yes.
Well, that is wonderful to hear about how you like to spend your time with your family, enjoying the great outdoors when you're not working. Those, few science-free moments of your life, perhaps. So can you tell us next about what you do in the lab, and how do you describe what you do to someone who might not be in science?
Yeah, our research is really a curious thing because we have to use a very complicated phrase, nuclear magnetic resonance. A couple of those words might not be familiar. The word nuclear doesn't always inspire, friendly associations, unfortunately. Yeah, and confidence. So it's actually very closely related to a technique that many listeners might be familiar with, which is MRI, magnetic resonance imaging. And most of us have either a friend or a relative, or even ourselves have been in an MRI machine in a hospital. And of course, that's a way of imaging your internal organs and soft tissues and all sorts of things that are hard to see by other means. Now imagine, instead of looking at people, that same set of tools would be really great for looking at a whole host of other things. So I'm what's called a materials scientist, which means I study the chemistry, the physics, the engineering of things of daily life. And what I mean by that is stuff as simple as plastics, things like the semiconductors that control the flow of electrons in computers. And so there's a whole bunch of different things that one can learn by looking at those different materials by using my technique, which we call NMR, nuclear magnetic resonance, but again is a cousin to this MRI technique.
Well, that is an excellent description of what you do, really making it accessible for people. And I think a lot of these, chemistry and physics types fields are intimidating to people who may not be familiar with the lingo. So I think you did a great job of making it accessible. And now, Sophia, I always like to chat with scientists. In addition to some of these research questions they're answering outside the lab, we talked about all the different activities that you like to do when you're not working. And I think balancing can be a challenge. So can you tell us today how you get everything done in a day? Do you have a particular motivational quote or maybe a saying that you love to keep in your mind that really helps keep you focused and motivated?
Oh, goodness. I don't know about for getting everything done in the day. It's funny. There's no good quote to encapsulate the complete panic that comes with a faculty member's job of teaching and research and so forth. You never get it all done, I think is perhaps my words of wisdom, not a motivational quote. No, I think a quote that has stayed with me, and I have to thank my 10th grade English teacher. I considered becoming a literature major after having a wonderful experience in a English lit, American lit kind of class. And there's this quote that stuck with me, even from those early years, which is, "The strongest man in the world is he who stands alone." And I think it was Henrik Ibsen in a play. But that's such a great quote. And maybe you could look at it as being motivational. But the truth is, we scientists sometimes have to be that person who is pushing the boundaries of things and pushing new theories or new ideas out there. And you have to have that strength to be solo at times. Now, I love being parts of teams. I'm on 2 wonderful group projects, one out of Oregon and one out of Georgia Tech. And these are massive teams of many scientists. And that's actually my preferred way of doing research. Nevertheless, there are many times in a faculty member's life, teaching and research and getting tenure, where you really have to have that strength, if you will, to go it alone. So that's my motivational quote, perhaps.
I think that is an excellent motivational quote. And I think, Sophia, you brought up some great points in terms of what a scientist goes through in their career. These moments where you're working with a team, where you're part of a team, but also actually quite a few of these moments where you are standing alone and you have to find the strength to do it. I mean, even getting up and presenting your research in front of people, you're often standing alone and often getting a lot of feedback.
No, good point, Marie. That's true.
Certainly. Well, that is a great motivational quote to take with you throughout your day in science. Now, can you tell us a little bit more about maybe some of the people along your journey who've inspired you or served as role models?
Oh, gosh. It's hard to name any one because, of course, I was inspired by research that I saw as a grad student. There's a mentor of mine from Germany, Dieter Suter, who is fearless. He works on ideas that are at the interface between 2 different disciplines. He's a chemist who is in a physics department, one of the top physics departments in Germany. He combines lasers with other magnetic resonance techniques, and that inspired much of my research. I use lasers and NMR together. And so I was certainly motivated by that intellectually, and I was exposed to those ideas early on, unexpectedly, while in Germany during my graduate years, and it just changed the course of my research direction. And I think that I have him to thank for that, because I saw his creativity coming into play and the fearlessness that he used to address research. But I have to say, in terms of a role model, I think this is the first time I'll have said this, that, my mom was a wonderful, super hardworking woman who became a career person midway through my childhood. I have to reflect and say she was a great role model because she showed me what the value is of that type of hard work and dedication to support our family. And I think that that really imprinted strongly on me today. That's how I am able to have this job and do many things, is because I think I got a great work ethic by having her show me that that was doable, and still being a parent and the like. So both of those role models were strong ones for me.
Well, that is wonderful to hear about some of these people who really inspired you, who served as role models throughout your life and throughout your career. And I think these are two great examples. Someone who scientifically really inspired you to think creatively, to work on the edge of a lot of different fields. I think that is fantastic. So can you tell us, have you had some challenges, or are there particular things that you have to keep in mind really working at the intersection of chemistry and physics and material science and engineering, or even ways that you have to modify how you talk to people within these different fields to accommodate it?
Yeah, you hit on the point exactly. So there's a certain language, if you will, to each of those disciplines. And I think if you read much of the sort of commentary on science that's coming out about communicating science to others and how we are able to make advances because we can share ideas better, I think that that is one of the focal points for me and my research group. We spend as much time in the physics department here at Washington University as we do within chemistry. We have enormous ties to engineering, and that has completely changed the nature of research we do. And so in part, that's because my wonderful grad students have facility to do this, and they have personalities that allow them to reach across disciplines and feel like they can contribute while still having this strong underpinning of chemistry, which is, of course, their core training. So the whole is better than the sum of its parts, if you will. And so there are things that we tap into by, again, working across disciplines.
That is a really important challenge for people to keep in mind. You know, communicating science, oftentimes every field has their own sort of vocabulary and things you have to learn. So it's great to hear that you've almost established a multilingual group there in your lab.
Yeah, that's funny. That's a good way to put it. I like it.
And great to hear about how your mom really inspired you and was able to really teach you this amazing work ethic that I think so many scientists need to have to even try and make a dent in that to-do list every day. And now I'm curious to hear about where your interest in science really began, how you started becoming interested in the field of chemistry, maybe in particular, or in science in general.
You know, I think you hear this from many people. There's always this interest in science if you grow up and are exposed to science museums and programs like NOVA and Cosmos back when I was a kid, you know, the Carl Sagan Cosmos, not the Neil deGrasse Tyson one.
Right.
And, you know, there is always this encouragement of intellectual curiosity, and you climb up the ladder taking the courses that support that, you know, throughout junior high and high school. And I would simply say that just feeding that curiosity and allowing it to grow allows you to develop, you know, those interests and those skills. My particular interest in chemistry, interesting, you're going to laugh, but I didn't have high school chemistry.
Really?
And so I went and took freshman chem right off the bat, and it was one of the hardest courses I ever took. There's this assumption that you know a certain amount of chemistry when you come in, and I have to say it was daunting, but I found that the subjects were things I gravitated towards. That and physics, both. And I feel that I got into this area because I did undergraduate research in a materials science lab. A professor who was at my undergrad institution named Bruce Novak, who's moved around a bit since. And through exposure to that type of science, I ended up, you know, going on a track towards grad school and chemistry in the end. So it's like the drunken walk pathway of diffusing around and trying different things, sampling different techniques, and you end up perhaps finding the path that works best for you.
Certainly. You wander around until you find something interesting and stay there. I like it.
Pretty much. Or sample different things until you find the one that works well. So yeah, I was really fortunate in that way because there were many opportunities at Berkeley for undergrad research and to get exposed to a wide variety of classes. And so Washington University offers similar kinds of things. Lots of undergrad research again, and people are encouraged to sample a number of different courses to find what they like best. So
I love chatting with people, and when they talk about their interest in science, it's really hard to pinpoint where it started. I think a lot of us feel like you were born to be a scientist. You were just naturally curious and drawn to these things. So interesting to hear about your journey. And I am very impressed, Sophia. I can't imagine trying to take freshman year chemistry without having it in high school. I struggled enough having AP chemistry background before I came in. So
I fear it was just by necessity. Yeah. You had to take it when you got in, and that was it. So
just put your head down.
Anything to be, yeah, exactly. Had to do it.
Gotcha. Well, wonderful to hear about your journey and how you got to where you are today, becoming interested in the world of chemistry and really getting this interdisciplinary play with all these different fields coming together. So can you tell us in a little bit more detail about one of these projects that you're working on that you are thrilled about?
Yeah, this is going to be the one that's hardest to talk about, I fear. The one that perhaps motivates me the most is the combination of lasers with magnetic resonance. And so for parts of your audience that know a bit about, let's say, chemistry and physics, I guess a way to describe that would be the lasers create something like an excited state. And what that means is you take a molecule or a solid or something, and let's just say that you shine a laser at it, and in some cases that might make the object glow. Some of us are familiar with that type of effect, but that's not actually what's going on here. But if you can picture that sort of effect, imagine that while it's glowing, you could take specific snapshots. We call it taking spectra of what that looks like. And it turns out that the glowing object is not like the object when it started out, before the laser hit it. And so it turns out that using our technique of NMR to look at the object after the laser has hit it results in very different phenomena. And so where it's important are for things that are familiar to you in everyday life. Solar cells, things like the photodetectors in your iPhone and in other types of media. Realize that when light strikes those objects, what it's doing is it's creating electrons, and the electrons move within the material. That's why we have the images that we do on the iPhone. That's why in solar energy cells, it creates a photocurrent that we then extract as electricity. Well, in that process, if you could see what the electrons are doing and have a window into that, that's what we're really trying to develop. So the things that we are trying to achieve here are, let's just say, a new measurement modality for looking at those processes, one that doesn't exist yet. And so we're in the developmental stages. We're the ones who are maybe trying to understand how those measurements might work so that I hope a later generation of scientists can come along and use it in new and creative ways that maybe I and my group haven't thought of yet. But we're showing how the technique might be able to function.
Very interesting. Well, this is a fascinating project. And, you mentioned the application within sort of solar cells, photodetectors, semiconductors, all these different things that are incorporated into electronic materials. Is this something where you think your technique is going to give you information that will help optimize the performance of these sorts of things?
Yeah, that's a really good insight. Indeed. In other words, why do it if it doesn't necessarily help us improve something about the material or the quality of life, if you will? Yes, one would hope that the behavior of those electrons within the material then can be, let's say, diagnosed. Much as an MRI is used to diagnose a patient in a machine, if you had ways to look at the electrons specifically and see maybe if they stuck somewhere within the material, those are the kinds of things that the technique, and I haven't named it, it's called optically pumped NMR, OP-NMR. So in OP-NMR, the desire there is that we find some information out, perhaps about those electrons. I'm just going to say there's another curious phenomenon that comes along for the ride, if you will.
Sure.
It turns out that those electrons, not only might we be able to see where they go, but they have an interesting effect of, let's say, enhancing signals in certain areas of the sample. Again, some creative minds have suggested it, that we can use that enhancement as a way to, let's say, light up something that would otherwise be dark. We might be able to see things that are otherwise obscured to us. And so it's this idea of transferring signals from one part of the sample to another in that kind of excited state. It's really hard, I have to confess, to discuss this without quantum mechanics,
right?
Which we rely on, when we train our grad students in these kinds of processes. But in essence, all the things I'm saying are underlying that quantum mechanical description. So it's the idea that you can, again, light up an area of the sample, see where that occurs, but maybe you can use it in new and different ways. So OP-NMR has a lot of promise in both of those areas.
Definitely. Well, it sounds like this is a really exciting project where, you're right, it could have a lot of different applications to really understand what is going on in this process with these electrons, and then maybe further down the line be able to apply it to some really fascinating technological solutions. I think that's really cool. So exciting to hear about one of these projects that you're working on now. And I think so far, Sophia, we've talked about a lot of the great aspects of your career and just your journey as a scientist in general. And I think every scientist has dark days in addition to these fun, exciting days as well. But we like to talk about these just because I think in the media, when you're talking to scientists, you hear a lot about the success stories. You hear about the amazing discoveries, great things that are happening, and you don't often get a glimpse of what is happening behind the scenes, the struggles, the challenges. So we like to talk about those as well. Can you take us back to a point in your career where you were struggling with something, or maybe you had a major failure, and tell us what happened and what are some of these steps that you took to really get through it?
Oh gosh, I have to confess that as an instrument building lab, we have regular failures. And so I suppose it's not that there was any one dark day, so to speak, but I fear there are many gray days, quite a few that are stormy and cloudy. I think any one incident, in my case, my grad students and postdocs are really pushing the envelope on a lot of equipment. We go to 4 Kelvin, and that's basically the temperature of outer space using liquid helium to cool our samples. And we have high-powered lasers, and we build radio frequency hardware that are controlled by massive amplifiers. So any one of these pieces may not be working on a given day. And so I think my students and I face something breaking down, and only one piece breaking down, and then the entire experiment has to be sort of shelved until it's repaired. And so I think perhaps the best answer to the dark days is that we simply step back. We understand that, the experiment's over for some time until the repair can be made. And then, well, it's like experiences I've had on sailboats too, where, something breaks and then you just have to sort of secure everything, make sure everybody's okay, other pieces of equipment are okay. And then like a checklist, you start going through and saying, let's solve the small things first. Then let's go for the bigger things. And then in a systematic way, we simply take care of the problem until it's resolved. Of course, on a sailboat, it's critical for maybe getting back to shore.
Right.
In our case, it's critical for getting back to work. I mean, it has to be fixed sooner or later. And sometimes we've had downtime as long as 6 months on occasion because of something inadvertent that happened. But the students, and I too, learn a fair amount of resilience in that process and learn that, hey, when something's broken, is there something else we can do in the meantime, to fill the days, do other experiments? And so I think that people in my group, because of these regular small things that come up and sometimes big things that come up, we find other ways to fill the time. That's been something very useful for my group and for me to keep our spirits up, if you will.
Definitely. Well, interesting to hear about one of these challenges that you face every day, just in terms of working with these extreme sort of cutting edge technologies at really harsh conditions. Man, 4 degrees Kelvin is quite cold.
Yeah, it's very cold.
Certainly. So I really like this methodical approach that you describe in terms of kind of taking stock of everything after something breaks, kind of see what works, see what's left, what can you do, make sure everyone's okay, and then work towards getting it put back together. So that is a phenomenal response to some of these times of challenge or perhaps trying times. Now, Sophia, you mentioned that there can be downtime of up to 6 months where you're not able to get a piece of equipment to work. So how do you occupy this time? What are some other things that you might do while you're waiting?
Well, fortunately, Maria, we have multiple projects in the group, and the OP NMR that I described is only a third of the work that we do. We have 2 other major projects that are ongoing. One area of research, about a third of the effort for my group, is in carbon capture, utilization, and sequestration. That's the idea of taking carbon dioxide, or CO2, out of the atmosphere, finding ways to capture it in flue gas with special materials, and also putting it underground to sequester it, or to have it go from carbon dioxide in a chemical reaction to form carbonates. And a carbonate is something like calcium carbonate or magnesium carbonate, the things that make up limestone or coral or magnesite, those minerals. And so underground, the hope is that it's a way of cleaning up that greenhouse gas. So that's, again, about a third of level of effort in my group. Another third is working on what are considered thin films that are grown on top of semiconductors. They have a technical name called high-K dielectrics. And what they are is they're the insulating layer that are used in semiconductor chips. It's the thing that keeps the electrons inside, if you will, inside the metallic portions or semiconductor portions of the chip that carry the current. It's extraordinarily important because they try to make smaller and smaller semiconductor devices. These materials have harder and harder performance metrics. And so NMR is being used as part of a massive team effort to study these metal oxide types of layers. And so those are two other areas where my students keep busy, if you will, if one experiment is down for a bit. So we have multiple projects going on all the time.
Certainly. Well, it is great to hear these different strategies that you employ to help you get through these tough times, these struggles when something breaks. I think definitely that methodical approach of going through, seeing what's salvageable, what's able to be fixed, making sure everyone's okay, things like that, very important. But then also really having this diverse portfolio of different projects that you can work on while maybe one of them is down. So great to hear how you deal with some of these tough times, Sophia. And we don't just want to focus on the challenges that scientists face. So can you tell us next about one of these success stories from your lab, something that maybe has happened recently that you've been really excited about?
Oh, yeah. I'm glad you asked. We are very excited because in the world of NMR and in the world of MRI, there are usually only a few nuclei that are looked at very often. And when I say nuclei, these are just how we take those photos, if you will, to use a colloquial term, or the spectra of things like protons, which are the hydrogen nucleus, if you will, and also of carbon. And so those are the two most commonly studied species. In my group, we do exotic nuclei. And what I mean by that is we look at things from the periodic table that are less familiar, things like cadmium and gallium and aluminum and all sorts of other atoms, nuclei that are less familiar to most chemists even, truthfully. And so in my group, we recently completed a study on gallium. There are two isotopes that we look at by NMR, gallium-69 and gallium-71. And we were struck because this is a nucleus that many people don't study because it's just really hard to do. It's got some physical properties that make it sort of difficult to elucidate its structure. And what happened is we got very lucky with a synthetic team out of University of Oregon and Oregon State. They were making gallium oxide style clusters. And because the purity of the samples was so good, we were able to obtain truly beautiful gallium spectra. And you have to understand that this nucleus was not accessible to us perhaps a decade ago. It's the advent of new technology and new techniques from colleagues in the field, as well as high field instruments, very high magnetic fields. And these are at facilities around the country that allow us to travel and use these high field instruments and give them a shot. So in summary, we were able to look at this metal oxide molecular clusters. And through that, we were able to get these beautiful structures that had never been seen before. And so that was recently published in Chemistry of Materials. And we were excited to now look at the films that are grown from those clusters. So lots of exciting developments there. And that's in this area that we call high-K dielectrics.
Well, that sounds like a fantastic success there. So what did you do, or what was going through your mind that moment when you first set eyes on these beautiful gallium spectra, as you described them?
Well, I must tell you, the spectra are highly complex, and my students worked doggedly with other scientists. In fact, we got some great advice from some other colleagues in the field. And in and of themselves, the spectra have peaks and valleys and shapes to them, and we try to tease out the details. It's sort of like seeing the silhouette of a set of mountain peaks and trying to figure out who's the mountain in the front and who's the range in the back, but you're looking at it at sunset, so you can't really figure out any depth perception. Mm-hmm. By the same token, we try to tease out those shapes, and actually the beauty came only when my students managed to fit that silhouette to a series of 3 different lines. And it's not just a simple line, it's a line with their own peaks and valleys and separating them each into individual patterns. And so I think the eureka moment was, oh my gosh, you got it to all converge to a single picture. So they had a crystal structure match up with the spectra. That was a great moment. I was really proud of my group when they figured it out and came to me to show me what they had managed to do. It was really something.
Well, that sounds like a phenomenal team effort there. Everyone putting together all these pieces. And I think that analogy is perfect. The sort of looking at this range of mountain peaks when the sun's setting, when it's dark, you only see the silhouettes and then having to sort of piece everything together, how everything's arranged. I think that's incredible. So great to hear about one of these successes. And I know scientists keep so busy with a lot of the work that they're doing in the lab that they don't often have time to relax and enjoy a good book. But I have met so many avid reader scientists and gotten great recommendations. So can you add one to our list today, Sophia, a book that you've read and really enjoyed?
Oh, I told you earlier I was almost a literature major, so
I know.
I just can't pick a single one, but I'll simply say on the shelf in my office is a combination of a couple of titles. I really enjoy the short stories of Ernest Hemingway, and I find that maybe in those short breaks, if I have a few minutes where I just want to decompress, I can pick that up again and again, and I love his prose. So I would say that's perhaps the one that I would point to.
Well, wonderful recommendation. I know I almost feel like someone's asking you to pick a favorite child when they ask your favorite book. If you're a literature enthusiast, you're like, well, I can't pick just one.
Well, and it's also the mood for the day. And, I think we as scientists look to equations to help describe what we do. And yet words have so much power, individual words. And so writing to me is extraordinarily important, and writing well and picking words well. So poetry, for example, I really love, because if you think about it in only a few lines, you can communicate a mood, an idea, a complex set of things, and it's only in a few spare words. So we science writing folks have something to learn from those worlds, I think.
Certainly. I think concise is often the name of the game in science trying to write. So, well, great recommendations, Sophia. I'll put those out on our website on our resources tab for our listeners to find. And it's exciting to talk to scientists about the different opportunities that they've had throughout their career to do amazing research, but also to go to amazing places. A lot of conferences where scientists are sharing their research are in phenomenal venues, and even just the places that you might travel to work with collaborators or things like that. So can you think back now, Sophia, over all of the places that you've traveled for science, and tell us next about your favorite place?
Oh, hands down, it has to be Chamonix in the Alps. And the reason is that's the Alpine meeting. They were kind enough to give me an award at that conference. But it's simply a wonderful meeting of European scientists as well as American and counterparts actually from all over the world, Asia as well. It's a small meeting, and it's very intense. There are excellent talks, but also poster sessions, and some of the discussions that I've had there have been extraordinary and have taken my research in different directions. It's in an absolutely breathtaking valley, of course, in the Savoie. And so there's wonderful scenery, great food during the conference, wonderful people to be with. And so it's like summer camp for a group of scientists, a smallish group of maybe 200. And so you get a very intense experience for those 5 days when you're there at the meeting. So,
well, that sounds like a wonderful place to be able to travel. Now, you mentioned you were there for about 5 days for the meeting. Are you able to extend your trip at all to maybe do any skiing or anything afterwards?
Well, it's in summer and they have perhaps not a skiing season. There's some great hiking in the area. Usually, I sadly cannot spend extra time. I mean, with my to-do list back home, I'm not often able to linger very long, but I do often link a trip overseas like that to visits to companion labs, if you will, or collaborating labs. So I usually end up in somebody else's basement looking at another set of data or looking at an instrument on either end of such a meeting. So, well,
I think that's a great opportunity too, then forming some collaborations, being able to work with people across the seas. That's wonderful. So great to hear about this incredible travel experience that you've had, and exciting. I think these smaller conferences, you're describing about 200 scientists, where you really get to chat with people, really get to bond over research, I think, compared to maybe some of the larger conferences you go to. So great to hear about these experiences. And I think speaking of the people in science, I think oftentimes you get opportunities to work with just amazing, creative, and often very funny people in these different lab groups that you work in over the years throughout your scientific training, things like that. And I know that there are stereotypes out there about what scientists are like, and we're trying to break those with our show. So we like to talk about the human side of science. And I know people take the research very seriously, but you also have fun. So I like to chat with people about maybe some of the fun memories in science, or even some of these quirky traditions that spring up in the different groups that they've worked in. So can you share one with us today, Sophia?
Oh, I don't know if we have many lab traditions per se. Oh, we do have one that I can point to, which is when each grad student passes their PhD, there's normally a reception. Cake and champagne is the norm. But what we do in my group, we adopted from University of Dortmund in Germany, and this was Dieter Suter's group. We build what's called a doctor hat. So it's like a graduation cap. But on the cap are all sorts of things that are inside jokes just for the person who is graduating. And so there's a combination usually of something mechanical or that lights up or does something on the hat. It usually is a mix of science references, if you will, to their career, as well as some personal ones having to do with their penchant for pizza or the fact that they really liked rock climbing. And so there's a mix of inside group jokes and larger jokes within our grad student community and department that tie in a lot of people. And it's kept, of course, secret up until the PhD. So everyone knows they're going to get it. But when it comes out, it's always funny to see what people associate with you.
Interesting.
As your funny foibles as well as triumphs. And so it's really perhaps the best and only tradition maybe in my group.
So what is the craziest thing or maybe assembly of things that has ever happened on one of these hats?
Oh, somebody had a little bit of a fog-making liquid nitrogen sort of thing. So it made a little bit of fog, and there was a light in the middle of it that would light up when the person pushed a certain button, and it was just quite complicated, and it was meant to simulate one aspect of their research. Sometimes it gets really detailed, and, people talk about having these in their office somewhere, even later on after they've left the group. So
you can put your thinking cap on anytime when you're in a pinch.
Yeah, exactly.
Well, I love that tradition. I think that's a great opportunity for scientists to get a little creative too, to kind of put something together, think back on all these memories that you shared with the people who are graduating and really assemble something meaningful. That's a wonderful tradition. So great to hear about some of the fun things that you're able to do in the lab, and exciting to hear that you've kept this tradition going from your time in Germany. So can you tell us a little bit about what it was like to be at the University of Dortmund for some of your postdoctoral research?
Oh gosh, how could I encapsulate such an immersive experience? I entered a group that was very technically trained and gifted. I think the funniest story was, and I hope it's okay to tell this on the air,
Sure.
is that the group leader declared that his whole group speaks English, no problem. I should be able to come there, no troubles, and get experiments going. But when I came down to lab, the students were not pleased to see a person from overseas coming in to visit them and take over their experiments. And so they both looked sternly at me and said, well, if you want to do experiments, they happen only in German. And so they were laying down the gauntlet of a challenge,
Right.
if you will. And rather than running back to the group leader, which of course I could have done as a postdoc, no problem. Instead, I said, okay, you're on. So we did the painful process of me learning German roughly, using the laser table and the magnets and everything. And it was really something. In the end, we've become lifelong friends. And I learned German at perhaps a first grader's level, lack a lot of grammar, but becoming semi-conversant.
You just need those key vocab words, right?
Yeah, and there's some crazy ones. My group laughs now because I use the German words for many things on the laser table because that's the first that comes to mind. Mm-hmm. So they've learned a few of these words because I can't think of the English word. I learned the German one first. And then I have to sit there for a pause or two to remember what the term is in the other language. So it's kind of funny. And they've grown used to it, but they're all of good humor on both sides of the Atlantic. So
certainly. Well, that is really interesting to hear how you had to learn German firsthand. I think you're exactly right. A lot of this technical jargon, I think, doesn't even translate well necessarily. So And I know we've chatted today about some of the research questions that you've worked on over the years and some of the projects that you're working on now. But I also like to talk to scientists about some of these dream projects that they would love to work on, but there might be things standing in the way. So things like funding and staff and technology feasibility, the minor details that constrain your research. So can you tell us, Sophia, if we took all of these constraints away, what is one question that you are dying to know the answer to?
I have become fascinated with the study of this project that I referred to about converting carbon dioxide into carbonates. This is an area of enormous importance worldwide. And if we were to come up with a safe, economical solution, in something like a Manhattan Project style team, if you will, to solve this problem, I think that that's where I would put my effort. There was an IPCC, International Panel on Climate Change, that came out many years ago that was very controversial in the early 2000s. And in this report, there was an unfortunate diagram that listed that these processes of what are called carbon dioxide mineralization, as it converts to the carbonate, would take, tens of thousands of years. And so this simple graphic that was meant as a cartoon illustrated, I guess, perhaps a bias in the field that, that this wasn't worth looking at. And yet this is the safest way of us capturing and storing the carbon dioxide in a way that's safe for us. There's a company out in California, a startup company named Calera, for example, that's trying to make calcium carbonates out of some of this gas coming from a power plant at Moss Landing. And it's that type of research that I think if you got everybody together, share information, and have the political will to do so, that would be the problem that I would work on. And we provide only one window into that, which is this NMR window to watch the process happen. Oh, and let me finish that statement. Clearly, it doesn't take 10,000 years. It's much too long for a grad student to get their PhD. And yet we're able to see such reactions on the scale of hours in our lab. Again, the conditions that we try to mimic are those that are found underground. And yet, if those conditions could be found in sites around the world, those would be, let's say, perfect environments for storing CO2. So my point is this. If money and resources and politics were no object, I think that that would be a problem that a multitude, a team, together would actually be able to find a solution that would yield something for the planet, if you will.
I think that is a really important area of research. And I think you brought some really interesting insights to this question, just in terms of what some of the limitations are, a lot of the maybe biases or political forces that are acting on it to make it a little bit more difficult to work towards a solution. So fascinating question for us to think about. And I know in addition to chatting about some of these big questions with the people in your field, your colleagues, your mentors, things like that, a lot of scientists get some great advice from all the people around them throughout their journey. Can you think back, Sophia, on all of the incredible advice that you've received over the years and tell us what you think is the best piece of advice?
I wish I could credit the person who told me this because I now do this for each junior faculty member coming into the department. There was someone who wisely told me to draw a pie chart on the board, and they drew a circle and put some wedges in it. And they said, at some point you're going to figure this out, but I'm going to tell you now so that you don't have to figure this out on your own. They said there's no way that you're going to make the entire pie happy. In other words, there's going to be a wedge of people in the pie who are maybe questioning or critical or whatever you want to say. And this can apply to anything, teaching, research, a bunch of different areas. And so they said, as soon as you figure out that you're not trying to get 100% of that pie chart aligned behind you, I think you're just going to be okay. You're going to be happier as a person. And I think that that's great advice because maybe that applies to a lot of things in life, in that if we, don't try for 100% solution of getting our colleagues behind us, and maybe we realize that it's hard to get that 100% consensus, I think that that is a useful tool in almost any role. Whether you're leading a group of people, whether you're the chair of a department, a dean, or whether you're just a faculty member trying to get tenure. All of those areas are helped by having this little picture in your mind of that pie chart with maybe one triangle, one slice taken out. And so I think that that was great advice that helped me kind of look at everything with a slightly different perspective.
Well, I love that you're able to put a visual behind it too. Draw this little pie chart and go into this piece of advice, which I think is phenomenal advice, in particular for people maybe just starting the science career, but really applies to all walks of life. You're never going to be able to make everybody happy all the time. You're never going to get that unanimous support. So you have to be happy with, maybe the 75% you have today or, whatever it might be, and just go with it and not try and please everyone all the time. So great piece of advice, Sophia. Is there any other last piece of advice or maybe a last piece of inspiration that you want to share with our listeners now, coming from you personally?
Oh, gosh. I hope you have young people listening because all I would want to say is the job that I have as a faculty member and those to-do lists sounds daunting at times, but it still is the best job in the world. I get to work with a group of students who each one comes with different skill sets. They leave with even more different skill sets, and yet it is wonderful to be able to work with this team of students and postdocs and colleagues, to achieve the goals of the science that we try to do, but also let us follow our scientific curiosity into places we never thought we would be. And so I think if I can encourage you by simply saying, keep that curiosity and keep following those funny pathways on that drunken walk, if you will, and diffusing around to different stuff until you find something that really works for you. And I haven't taken one particular path. I've taken a bunch of different ones, stopping and starting along the way. And I see that in my students as well. They don't all become scientists, by the way. Some of them become teachers, great teachers, actually. And some go into industry and national labs. One even works for the IAEA at the moment, the International Atomic Energy Agency. I think I'm getting parts of the acronym right, not all of it. And so the point is simply that you never know where it's going to lead you. But science allows a lot of doors to be open, and it teaches you ways to think about the world. So I think that that's a great thing.
Well said, Sophia. I think that is excellent advice and really inspiring for people to keep in mind that they are encouraged to follow their own path, not only through science, but through life, and to find something that they're really excited about, really happy about. And wonderful to hear that you are so happy in that current position that you're in. So, Sophia, I think we've had some great discussions today. Can you tell our listeners how they can reach out to learn more about you or your research?
Oh, I think the best way is, of course, there's a website at Washington University. Looking for Sophia and chemistry pretty much gets you to me very easily. It's easy to find me. Also by email, I'm happy to answer inquiries, sometimes with a little bit of a delay if I've got quite a bit in my inbox. But my email address is Hayes, Hayes, @wustl.edu. That's WUSTL.edu.
Fantastic. Well, listeners, feel free to send any questions that you might have to Sophia. And Sophia, thank you so much for joining us today and sharing a little bit about your story.
Well, thank you, Marie. I really appreciated the time to talk about this. Thank you so much.
Certainly. Well, this was a lot of fun for me as well. And thank you to our listeners for joining us today. We'll see you next time on another episode of People Behind the Science. Your voyage to the lives of today's exceptional scientists has just begun. You can find everything we talked about today, including our guests' favorite books, biographies, photos, and more, when you visit us at www.peoplebehindthescience.com. I look forward to seeing you next time on People Behind the Science.